Hello everyone, welcome to this video lesson. In this video lesson, we are solving a problem from mechanical properties of solids. Let me read out first of all what the problem is. The problem is like this. Length of a wire is L1 when a tension in it is T1, and the length of the wire is L2 when the tension in it is T2. What is the length of the wire when there is no tension acting in the wire? That's what the problem is. The first thing that we need to understand is who creates a tension in the wire. Obviously, if I am having a rigid support to which a wire is suspended, if there has to be a tension, then first of all there has to be a force acting in the wire. Then this force creates a tension in the wire. Both are equal in magnitude but opposite in direction. So I would like to say tension is nothing but equal to a force generated in the system. Then I can write the basic definition of Young's modulus. Young's modulus is defined as ratio of longitudinal stress to that of the longitudinal strain. That is rearranging the terms. So if I have to calculate the increase in the length delta L, that's nothing but equal to FL by AY. In our problem, length of the wire is not a variable, area of cross section is not variable, and Young's modulus is not variable. All of them are constants. So only F is variable, that is tension is variable. So I can say delta L is directly proportional to F. That's nothing but directly proportional to tension. Now coming to the problem, it was given in the problem that when the tension is T1, the length is L1. So it's very clear that whenever the tension is applied or whenever the force is applied, it is obvious that the wire will be having an extension, elongation. So the length given as L1 is not the original length, because it is when you have applied a tension, it will be having not only an original length but also a elongation also. Let that elongation in the first case is something like equal to delta L. Then delta L1, I would like to say elongation in the first case is L1 minus L0, as per this directly proportional to tension. Na? The tension in the first case is nothing but equal to T1. So when the tension is T2, it's obvious that the elongation will be different. Let that elongation is delta L2. That delta L2 is original length, mean the elongated length, that's the final length L2 minus L0. How do I have got it? When the tension is T2, the length is the final length, it's not the original length. That what is the final length? Original length plus increase in the length delta L2. So I will get delta L2 as L2 minus L0. So I got delta L2 as L1 minus L0. That's directly proportional to the tension. Let the tension in that case is T2 as per the given problem. So dividing these two equations, what I will get is L1 minus L0 is some constant into T1. L2 minus L0 is the same constant into T2. Dividing these two equations further, L1 minus L0 by L2 minus L0 is T1 by T2. Now, what value? The condition is when there is no tension is applied. When there is no tension is applied, obviously the force is nothing but there is no force. Then the length is nothing but the original length. That's nothing but L0 in our problem. I have to calculate that. Let's cross multiply this. So I will get L1 T2 minus L0 T2 here equal to here L2 T1 minus L0 T1. So getting that L0 term this side, it will become plus L0 T1 minus L0 T2 equal to L2 T1. Taking this term to other side, minus L1 T2. I can take L1 common, equal to L2 T1 minus L1 T2. That implies the original length L0 of the wire when there is no tension applied is L2 T1 minus L1 T2 by T1 minus T2. It can be also proved as L1 T2 minus L2 T1 by T1 minus T2 minus T1. Both of them are same. Thus, we can find the original length of the wire when there is no tension acting on the wire. All this is depending on basic definition of Young's modulus. That Young's modulus is the ratio of longitudinal stress to that of a longitudinal strain. Thank you for watching. Keep coming back for more and more video lessons. Thank you.